Welcome back to Cypress Academy PSoC 6 101. In the previous lessons, I showed you how to build BLE peripherals, specifically a peripheral running the immediate alert service and a peripheral running the custom service. In those lessons, we used your cell phone to talk to those devices. In this lesson, I'm going to show you how to create the other side of the connection. The other side is more properly called the central, or more specifically, the gap central. The way that a BLE central works is it starts by listening for advertising packets. This process is called scanning. When it hears a peripheral that is advertising something interesting, it can then initiate a connection to that device. After the connection is made, it can discover all of the services on that device, and after that's done, it can read and write characteristics on the remote device. You might have guessed from the previous lessons that there will be events that are called back to you each time to indicate that these steps have happened, and you'd be exactly right. With this project, I'm going to show you how to take care of each of these steps that I described earlier, and I'm going to show you how these events happen and when. You will then be able to program your development kit to see all of these things going on in BLE land. For this lesson, we will build a central that will look for the red LED brightness peripheral that we programmed in lesson 3.2. It would be better if you had two development kits, one programmed with the LED brightness peripheral firmware and one to do this lesson. If you don't, then by all means order one up from one of our partners, or you can just follow along and learn with me. This project will scan the BLE airwaves looking for a BLE peripheral that is advertising the LED brightness service. It will then connect to it, discover its services, and then it will use the plus and minus keys on the UART to change the brightness of the LED. All right, let's get started. To make things easier, we're first going to open up the simple BLE project and save the LED service so that we can use it again in this project. That way we don't have to type in all that UUID stuff. Go to the schematic, double click the BLE, click GAT settings, then click on the LED service. Next, press the little disk image and select Save Profile. Then save the profile as LED service to somewhere you're going to be able to find it again, like say on your desktop. Now close that project and create a new project called Simple BLE Central. First, let's edit the schematic. Add the BLE component, add a UART, and a digital output pin, which we'll call LED 9. Remember, I like to use LED 9 to indicate the presence or the absence of a BLE connection. Go ahead and change its name to LED 9, make the initial state high so that it begins the process off, and turn off the hardware connection. Now edit the BLE component. This time, instead of making a BLE peripheral, I will select BLE Central. Once again, I'll run this project in dual core mode. Next, you'll edit the GAT settings. In order to make the service discovery process work better, PSoC Creator gives you the ability to tell the BLE stack what services you're looking for during discovery. This is called a client profile. Unfortunately, we didn't give you the ability to add a custom service, so you need to do a little workaround. Right-click on the GAT and select Add Profile, then Find Me Locator GAT Client. Next, right-click on the immediate alert and pick Delete. Now that we have a blank client profile, the next step is to load the LED service that we saved into the file earlier. To do this, right-click on the client and say Add Service from File. Then pick the file led.service. When you expand the LED service, you should recognize all the stuff we set up earlier. Next, you can go to the gap settings. First, give this device a name, and then change the scan settings to always do fast scan. I ain't got time to wait, boys and girls, so I want to see the fast mode. Now apply that. I almost forgot to assign the pins, and I know Greg would laugh at me if I didn't get that done. So go to the DWR and assign the UART to P50 and P5.1 and the LED 9 to P13.7. As I have in all of our projects, I'm going to use FreeRTOS and the Retarget IO library. So go to the build settings and include those into the project. Now hit Generate Application so that PSoC Creator can do its magic. Next, I'll update the standard IO user.h and tell it to include the project.h and use the UART_1 hardware as the standard in and standard out. In the FreeRTOS configuration, get rid of the warning, turn on semaphores, make a bigger heap, and change the max syscall interrupt, just like we did in the prior BLE projects. The next step is to set up and fix the main CM0P.C so that it runs the BLE controller. So turn on the BLE stack, then in the infinite loop, process events like that. Finally, we're ready to do some programming. My favorite part. Open main_cm4.c. This whole program will have three interesting functions. First, write LED, which will take a value as an input. Then if you're connected, it will write that value into the BLE peripheral that you are connected to. So let's write this function. Let's see. Returns a void. Function name is, write LED. Takes a uint8 as a parameter, which we'll call brightness. Now, let's ask the BLE if we're connected, and if we have completed the service discovery. In other words, we are connected, and we know the BLE handle of the green LED brightness characteristic. If that isn't true, then just print a message saying, no way, and return. So now we know we're connected. Print out that we're writing to the brightness. In order to send a BLE write, you need to call the function cy BLE GATC write characteristic. GATC means GAT client. In order to call that function, we need to have a structure of type cystc BLE GATC write request type. That structure contains all of the information about the characteristic that I want to write to. Each characteristic in the GAT server, which is running on the GAT peripheral, is identified by a 128-bit UUID, and that's a bunch of bytes, actually 16. Rather than send 16 bytes in every BLE transaction, we will create a 1-byte alias. That 1-byte alias is called the handle. The mapping of handles to UUIDs is sorted out during the service discovery process, which I'll tell you more about in just a few minutes. The bottom line is that for us to write the LED brightness characteristic, we need to specify the correct handle. And it turns out that the Cypress BLE stack figures that out for you and stores it in this crazy array. This is the first thing that we have to save in our structure. Next, we need to give a pointer to the value. We need to tell it how long it is. uint8, 1 byte. Those both go in our structure next. Then we need to tell it which connection. Remember, when we set things up, we configured only for one connection at a time, so I hard-coded the connection. Now that's the last bit of information that our structure needs. Once all of that is set up, I can finally call the write function, and if it doesn't work, I just print out an error. The next function we will write is called findADVinfo. This function parses through a BLE advertising packet and looks for the name and the service UUID. The format of these advertising packets is specified by the Bluetooth SIG, but it's pretty simple. When you get an advertising packet, you know its total length. The packet is then divided up into a variable number of fields. The first byte is the length of the first field. The second byte is the type of the field. Then the next length minus 1 bytes is the actual data in the field. This means you can scan through the packet and look at each of the fields to find out what you're looking for. Luckily, the Cypress BLE component has a cool tool for looking at advertising packets. Let me show you the advertising packet that you specified in the simple BLE peripheral. First, open the project, then open the schematic, then double-click on the BLE, then go to the gap settings, and finally to the advertising packet. This is cool. You can see the total length of the packet is 28 bytes. It has 3 fields in it. The first field is 3 bytes long, the second is 7, and the last is 18 bytes long. On this tool, you can see the other types of fields. All of these fields are specified by the Bluetooth SIG, but I'm really only interested in the name field, which you can see right here is 0x09, and the service UUID field, which is 0x07. Now that we know the advertising packet format, let's go write a parser. First, I'm going to store the name and the name length and the UUID and the UUID length into a structure. So let's declare that structure. Then I'm going to make a function which will return a void and will take a pointer to an array of data of type uint8. Those are just the raw bytes of the advertising packet and the length of the packet. First, I'll zero out my structure. Then I'll use a for loop to look through the packet. The first byte, aka ADVI, is the length, and ADVI plus 1 is the field type. So look at the first field type. If it's a 7 or a 9, then save the information about it. Otherwise, jump to the next field. Cool. When I get an advertising packet, now I can just look for the names and the service UUIDs. All right, the next function is the event handler. The function just looks like every other event handler that we've already built. If I get a stack on or a disconnected, then I want to turn off the connection LED and start scanning again. What this will do is tell the BLE radio to start listening for advertising packets. And when it hears one, it will call the event CYBLE event GAPC scan progress to tell us that it's heard another device. So let's deal with that event. On the UART, I will print out that I heard the device. Then I'll print out the BD address, also known as the Bluetooth address, and the length of the packet. Next, I'll call our handy dandy advertising packet parser function, which will figure out if the device has a name or its advertising service UUID. I pass it the raw advertising packet and the length of the packet. If it has a name, I'll print it out. If it is advertising that it has an LED service, I'll print out that I found a device that I can connect to, and I'll start the connection process with the Connect Device API, and then I'll stop scanning. The next interesting event occurs when a connection is made. That event is called CYBLE Event GAT Connect. When that event happens, I'll turn on LED 9 and start the service discovery process. Remember earlier I told you that I need to find the handles of the characteristics. That's exactly what happens inside of the start discovery function. Once that process is complete, it will give you the event discovery complete. The other interesting events, error response, write response, occur when a write is successful or when one fails. Now I need the BLE task and main. The BLE task starts the stack, then prints out a message. In the loop, it calls process events. Then if there's data in the UART RX FIFO, in other words, someone has pressed a key, it will read the character. If the character was a plus, it'll increase the brightness, and if it's a minus, it will decrease the brightness. The last function is main. It just turns on the UART, starts the BLE task, and starts the RTOS scheduler. All right, that was a bunch. Let's program this bad boy and see if it works. You can see that I have 2 development kits here. The one that I just programmed, plus the one is programmed with the simple BLE peripheral LED dimmer firmware. Let's open a terminal window and see what it says. First, we see that it starts. Then we see a bunch of BLE devices. And finally, it finds one that we're looking for, and it makes the connection. Then I can see the service discovery has completed. And you can see that LED 9 is active on the central, and the red LED has stopped blinking on the peripheral. So they're both connected. That's great. Now let's see here. Plus, 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 plus. I see that the brightness is increasing, and then look, minus, 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 minus. What do you know? It goes down. If I hold reset on the peripheral, you'll see that the central disconnects and starts scanning again after about 10 seconds. That's because the connection supervision timeout in the gap settings under the connection parameters is set to the default of 10 seconds. Once that timeout happens, it turns off LED 9 and starts searching again. When I let go of the reset quicker than anything, it finds the peripheral and reconnects, and now we're rolling again. Personally, I think it's pretty damn cool. Hopefully you can see how we might make a remote control for the robot, which is exactly what we're going to do in the next video. As always, you can post your comments and your questions in our PSoC 6 community forum, or you can email me at alan_hawse@cypress.com or tweet me at AskIoTExpert with your comments, suggestions, criticisms, and questions. And the first person who makes it to here, who sends me an email, I'll send you a PSoC 6 development kit. The first person. Thank you very much.